I have to admit that these problems have grown on me since I wrote the notes for them. We're using the second fundamental theorem of calculus. Your giant flashing neon sign that you're using the second fundamental theorem is that you're taking the derivative of an integral and that these variables do not match. Let's take a look at this. They're very, very simple to work. The first thing that you check is you make sure that your lower limit is a constant. It can be any number, including pi, any number. And if this is a single variable, then all you have to do is replace that variable in your function. And so this whole thing is equal to the sine of x plus x squared. Done. It really is that easy. But of course we gotta complicate it, so let's look at another one. This is the exact same problem, except for my limits are flipped. If I look here, my bottom limit is not a constant, so I can't go straight to switching the variables. But if I look at my top limit, I see that it is a constant. And so I think if only this was flipped over, then I could just switch the variables. Well, what can I do to flip over the limits? I know I can just make the whole integral negative. It's one of my properties of integrals. So I can rewrite this. I can say the derivative of the negative integral from 2 to x of the sine of t plus t squared dt. And now when I look, I have a constant, I have a single variable, I can replace my variables. And this negative doesn't really trip me up that much because I know that I can pull a negative out in front of a derivative. And so I just have to carry it along. So this is all equal to the negative of replacing my variables. And you could leave your answer like that, or you could distribute your negative, whatever makes you happy. You can make this the sine of x minus x squared. And it's done. Let's do another one. We want to apply the second derivative, second fundamental theorem of calculus. If I look at my limits here, I have a constant, but here, this is not just a variable, it's a function, which means that I have to take my answer and I have to multiply it by the derivative of that upper limit. And so I'm still going to take this and replace the t with that. So this is 2 times 3x instead of t, but now because this is a function, I have to multiply by its derivative. And so that is just 2 times 3 times 3 gives me 18x. And I'm done. Let's do one more. That's not what I want. I just want to add a slide. We'll come back to this problem. I want to do another one. I didn't make a slide for it. Just a little bit of practice with that. Let's say that I want to go from 5 to x cubed of the secant squared of t dt. I check. I've got a constant in the bottom. I've got a function on top. So I'm going to plug my function in for t, but then I have to multiply by its derivative. So all this is equal to the secant squared of, instead of t, I do my top limit, but then I have to multiply by this derivative, so by 3x squared. If I write that a little bit more neatly, it looks just like that. And it's done. Let's do another one. Let's see if I can go back to this one that I had. Here we go. If I look at the limits here, this is the integral from x to x squared of the cosine of t dt. And I've got a problem because I have a variable in the bottom and a function on top. There's no constant, so there's no flipping around to be done here. And so I have two options for how I can think about this integral. Option number one, think about this picture. If I had some function, don't know what it looks like, and I want to integrate from some x value to x squared. I don't know what x squared is, but it's going to be bigger than x, right? I could split this up into two separate pieces. There's some number between x and x squared. Doesn't matter what the number is, but I know there's some number between x and x squared. And so I could have this integral plus this integral, and I could get my total. And so I can rewrite this problem as the derivative of the integral from x to whatever that number was. You can pick a number if it makes you happy, of my function, plus the integral from that number up to x squared and now this looks like something that I can manage. This integral looks good to go. I've got a number, I've got a function. As long as I remember to multiply by its derivative, I'll be fine. This one, my variable's on the bottom and my number's on top, and so I know that I can put a negative out front and I can flip those. So let's write that again. Still got this derivative hanging out. Haven't forgotten that I'm doing the second fundamental theorem. So this is the negative integral of whatever that number was to x of cosine of t dt plus the integral from that number to x squared. I didn't have to flip this one, left it alone. And now I'm ready to go. So I'm going to leave that negative there. And so I can plug in x here. So this is cosine of x plus, and then I can plug this in for t. But it's a function, so I gotta multiply by its derivative. And I'm done. Just clean it up a little bit. That would be 2x cosine of x squared minus cosine of x. So if that conceptually makes sense to draw this picture and split up your integral, then go for it. But sometimes these limits get a little bit confusing, so I want to show you a second option for working this problem. Let me rewrite the problem. This was d dx integral from x to x squared of cosine of t dt. We need another way to think about this problem. So this is option number 2. Option number 2 is don't use any tricks. Don't even use the second fundamental theorem of calculus. Just work out the problem. Whenever you're working problems like this, you start with the inside and then deal with the outside. So I'm going to work the inside problem first. If I integrate cosine of t, if I take the antiderivative of cosine of t, I'm going to get the sine of t. Right, think backwards, the derivative of sine is cosine. Don't need a negative, so that works. And I need to evaluate that from x to x squared. And so I know I do my top limit minus my bottom limit. So I've applied the first fundamental theorem of calculus. I've dealt with my inside. And now I'm going to deal with my outside. I'm going to take the derivative of that answer. So if I take the derivative of the sine of x squared, that gives me the cosine of x squared. I gotta follow my chain rule, so multiply that by 2x. And then minus the derivative of sine is cosine. And I do believe that once I rewrite that, so that'll be 2x cosine of x squared minus the cosine of x. That should be the same answer that we got here. And it is. So, the picture is nice and easy if you can see it, if your limits make sense to do that, you know? If your limits don't make sense, or if you get confused, then just solve the problem. Integrate it, and then take the derivative. Skip the second fundamental theorem.